The work that I'm presenting is primarily the work of Han Peng, who was my PhD student, who is now back in Xiamen. So parallel adaptive high-resolution simulation of rotating detonation engines. So here, the outline of the talk. I'll give a brief introduction into this problem class, then how the solver works, some V and V, and then rotating detonation engine simulations. So in contrast to some of these flame computations before, this is about detonation waves. So in a detonation, we have shock-induced combustion. So it's a shock wave heating the mixture above ignition temperature and then a reaction zone. And what this causes in multi-dimensions, that you get these transverse waves that propagate along the detonation front that under regular boundary conditions form these, as we can see here, these very irregular cellular structures. And we'll come back to that later in the talk. But when they are present, that is a sign of detonation propagation. Yeah, so there is no detonation propagation without these cellular structures. So now let's talk about rotating detonation engines. Why are people interested in them? So detonation combustion is interesting because it would allow pressure gain combustion. So much higher efficiency of combustion engines than in the conventional flame-like deflagrative combustion. And the rotating detonation engine is one where the detonation front spins in an annular combustor, and it is a much more feasible approach than other ideas like the pulse detonation engine or the oblique detonation engine. So it promises high thermodynamic efficiency with a simplistic mechanical design. So here we see an RDE that corresponds to the one that we have built. So you see the annular combustor, and then the detonation wave here is typically initiated by a pre-detonator. Yeah, so the idea of igniting directly, for instance, with spark plugs in the combustion chamber, that doesn't work very well. So you need to create a shock wave that is shot tangentially into the engine. Yeah, and then of course we have continuous supply by the fuels, the propellants that would be mixing in the chamber. Yeah, so usually all practical RDEs that exist in laboratory are non-premixed configurations. So to illustrate that, here is an experiment from our own laboratory. So you see the annual combustion chamber here. Yeah, and then there's a pre-detonator who shoots tangentially into the engine. And yeah, this is how it looks like. Oh, there's actually sound. Yeah, so you see it. These engines make this very high hissing noise, and that is a shock, the detonation wave spinning around at Mach 6 in the engines, and there could be multiple fronts in this annular combustor. Yeah, so here we would see, so this is a very small engine, only 10 grams per second total flow. This is very, very small. And with a high-speed camera, we were able to record that it was 3 flame fronts. And then with some pressure transducer, we could deduce that the detonation velocity here is only 1,500 meters per second, which is a quasi-detonation. So considerably below the theoretically possible value. And that is also typical for such a small engine. So this is what we want to simulate. And we do this with our software system that I've been developing since quite some time. So it's called MROC, Adaptive Mesh Refinement in Object-Oriented C++. It uses hierarchical block-structured meshes to ensure mesh adaptivity. High resolution, local mesh adaptivity is particularly important for detonation waves because this interplay between shock and reaction front, you need to capture this with very high resolution. If you don't do that, already the detonation speed gets very wrong if you under-resolve that. So the original version of MROC, yeah, also published a bit a while ago, was using embedded boundary methods based on level set, yeah, so purely Cartesian techniques. However, here we are dealing with non-premixed combustion. We have to deal also potentially with boundary layers. If you imagine an annular combustion chamber with Cartesian grids, that would be quite some numerical accuracy loss that we would be encountering at the boundaries. So here we did something, we actually went back to a mapped mesh approach. So what we implemented here for this project is a mapped mesh on the block structured hierarchy that allows the capturing of the boundary, of course, with very good accuracy. So the solver works. The governing equations are the reactive Navier-Stokes equations that have to be solved here. So as I said before, RDE combustors are non-premixed. So particularly we need here the interspecies diffusion to be modeled correctly. So you can only do premixed archetypical RDE, so prototypical experiments with the Euler equation. So you really have to go to Navier-Stokes here. These are, of course, high-speed flows. So what we are developing are explicit finite volume methods. So this is not a low Mach number approach. This is fully compressible. Yeah, transport properties from Chemkin. Chemkin is also used for the evaluation. Few computational tricks. The CPs and the enthalpies, they are tabulated and then interpolated. Still, of course, in every finite volume cell, we need the temperature that is then evaluated from the state equation with a local implicit approach. And of course, we use source term splitting to integrate the chemistry. So you see here some, yeah, how did I do that? How do I go back from that here? Double touch. How do I just tipped on the screen. Very surprising. So the numerical method here for the local source term integration is a force order semi-implicit Runge-Kutta method. And there's another trick here. So the code uses Chemkin, and typically the reaction mechanisms, they're not evaluated by Chemkin directly, but they are specially generated Fortran mechanisms that are identical to Chemkin in numerical operation, but that speeds up the operation by a factor of 3 approximately. Yeah, so very standard computer science tricks that nowadays seems to have been forgotten. So here we want to construct now finite volume method on a mapped mesh. We do this with a capacity differencing approach. So in the finite volume formula, of course, then the volumes of the mapped cells and the area of the geometrically complex facets are included. The solver uses a transformation matrix T to rotate the velocities between computational Cartesian grid within the computer and then the physical grid. Yeah, so and here this transformation matrix then is used to transform back the computation. So in the physical velocities here to computational velocities in X and Y directions that are then fed back in the standard Cartesian Riemann solvers and then with T to the power of -1 transformed backwards. Yeah, so it's a second order solver with limiting and reconstruction on the convective fluxes and conventional second order central differences with coordinate transformation for the viscous fluxes. And because it's an explicit solver, this is all combined then in an according CFL condition. Considering, of course, then also here the smallest length scale on the mapped mesh. Yeah, for Riemann solvers, we have been using the row solver a lot. So that is a row solver for thermally perfect gases. We combine it typically with an HHL solver in case this solver goes negative. However, here for these computations, the RDE computations, particularly because we are dealing with a non-premixed situation, we have been primarily using the HHLC solver. So this is HHL with a restored contact discontinuity. And the reason for all of that is particularly when you have non-premixed combustion, there is a well-known instability that can arise at material interfaces between different gases in temperature and pressure, and the HHLC solver deals better with that. Of course, in order to do adaptive mesh refinement on the mapped mesh, we can use all our Cartesian AMR machinery because it works in IJK indices for the parallelization and creating the blocks and handling the blocks and so on. But of course, you need interpolation and restriction operation that consider the mapped mesh mapping. And there's also in this AMR approach, so you first integrate the coarser grades and then recursively the finer grades, and it leads typically to a mismatch of numerical fluxes at the interface, which is then corrected in a so-called fix-up, and that also needs to be extended to the mapped mesh, and only then you have a strictly conservative method. So here, quick VNV case. So this is a detonation going through a pipe band. It's already initialized with some cellular structure that we had simulated before. So here you see the efficiency of the AMR, so easily a factor of 50. That works very nicely because the detonation then here, so we see here Schlieren images and then here the levels of adaptivity, how it is going around. So the mesh follows very nicely the features. And here we see the cellular structures evolving through the computation. And here's some eyeball norm validation. So the decoupling of the detonation front, so the decoupling of the shock front from the reaction front, and that you get in this phenomena, you get a retonation wave that perpendicular reignites the partially decoupled region, and that works quite nicely. So let's now talk about rotating detonation engine simulations. So how do we do that? Of course, we don't have a pre-detonator in these computations. So we ignite and initiate the detonation wave with an analytic 1D detonation wave that is painted in the red region. And then this is also common, you inject fuel here triangularly. And that then starts the phenomenon. So here we see some typical physical features. Here the AMR. And now some visualization in 2D, how this would actually work in practice. So here you see the initialization. It starts as one wave. And then the system by its own, if enough fuel is available, it would develop a very regular configuration now here of 3 waves. And it's very important to understand you initiate one, and then the dynamic system on its own chooses as many waves as it can support. And of course, this is a little bit ill-posed what the system really would do. So this is when you have premixed injection. So 3 nice waves. And if we now do the same configuration as a non-premixed case, the mixing only then in this 2D domain, you see that actually only 1 wave actually develops. So and the mixing in these RDE configurations, that is about the most difficult bit. So now moving on to 3D. Here we simulated hydrogen air. The initialization is with a constant reactive layer, so we didn't use this triangular profile. So you see here a mesh refinement study using different levels of AMR, and at least always 3 waves are predicted. So you see here the number of CPU hours that are used, and for the highest resolved computation, almost 200,000. It's with dynamic mesh adaptivity, which we kind of see here. This is a 2-level case, so you see that the mesh is kind of changing and following also the flame front, the detonation fronts. And of course, one key question arises, how accurate is this? How does this compare actually with experimentation? And as I said, it's particularly the mixing that is the greatest unknown in RDE configurations. So generally, when you have a configuration where the mass flow rate is very large, like here, 860 grams in total, you see that the agreement between simulated detonation velocity and experimentally measured detonation velocity is very, very good. But if the mass flow is lower, then clearly the turbulent mixing is more complex, and there the description is larger. What you also can see is that the number of detonation heads can be different in the experiment versus the simulation. But what we need to understand is that in this system, the height of the detonation wave is also a variable. So depending on the amount of fuel available, if the system only shows 2 detonation waves, they would be higher versus if it shows 3 or 4 detonation waves. The height would go down. And so then the measure to compare is actually the combined and accumulated detonation height. And so here we see then actually good agreement. But how many waves it's really showing, that is a bit ill-posed. So, and I think people initially have been focused very much on this, but I think it is understood, I would say now, that this is not necessarily what you really have to look at always. So here now going back to our own simulation. So that was for hydrogen and oxygen. And here we now have, again, our configuration with ethylene and oxygen. So the computation, the highest resolved one, is using here 480 cores on the Archer 2 machine, 11 hours wall clock time. And here different levels of resolution. So these here are the exact same computations on the same resolution, once with 2 levels of AMR, once a uniform mesh. So here a benefit of a factor of 2. And then we can easily, on the number of cell size, we can go further up 1 resolution level. Yeah, and then you see the convergence. It actually is somewhat converged. And when we have that high resolution, we can actually make visible these detonation cells. Yeah, these multidimensional cellular structures, they would come into being also in such RDE configurations, and making them visible in a 3D configuration is actually an accomplishment. Very few people have actually done that. And here we have, we are showing these detonation cells. So what you would do is you can make them visible, for instance, in the heat release rate, or for instance, you record over time the maximal pressure. Of course, you can do this only until the next detonation wave arrives. This is why it is here for half a motion around the annular chamber, you can record that. So this is then depicted here. And then in the axial direction, so upwards, the size of these detonation cells is approximately 1.5 millimeters. But they are very straight, which is kind of an indication that they are still a little bit under-resolved. Yeah, so this is what the code is doing parallelization-wise. So our system uses rigorous domain decomposition. So all the workload is projected on the coarsest level. And then this is where the distribution algorithm operates. Yeah, so, and you see, so the mesh is changing, and then the distribution to processes indicated by colors is also changing wildly. So this is, of course, for an adaptive algorithm, that is a challenging problem because it is spinning around on its own. And you, of course, you have to do the redistribution and repartitioning all the time. There's no way around that. It's doing this dynamically with a space filling curve algorithm. And here we have depicted what happens before the repartitioning. We already have some noticeable load imbalance, then we do the repartitioning and the load is equally balanced again for a few more iterations. So I think here we repartition every 10 level 0 steps. Yeah, and the scaling on the Archer machine is actually quite all right. Yeah, and that basically brings me to the conclusion and the outlook. So what I've shown you is, so we developed the second order accurate code. MROC already had been used very extensively for detonation problems, but now we have this new version on curvilinear meshes, which for the Navier-Stokes equation is a decent accomplishment. So the benefit of AMR is quite apparent. So for the pipeband case, the factor of 50 in terms of cells, for the RDE simulations, kind of a factor of 10. And yeah, we can do RDE in premixed and particular non-premixed cases, and we have achieved reasonable validation. It still is a challenge to do this properly, to match experiment and simulation for these configurations perfectly. Yeah, and the reason for that is the origin is more physical. Yeah, so the simulations are very ideal, while the experiments also have some significant flaws. So the turbulent mixing, this is in my opinion the greatest influence on these configurations, is by far not as ideal in the experiments as you would hope to. There is of course also detonation boundary layer interaction and viscous boundary layer, particularly if the engine is very small. So the loss from viscosity can also be possibly not negligible, although nobody has really properly quantified this yet. Heat loss is very small. Yeah, so we have demonstrated that because all the energy is in the combustion in itself, you can cool these engines as you wish, and still you get effectively the same phenomena. We have demonstrated that in other publications. And of course, there is curvature effects, and that depends on the annular slit size versus the radius of the engine, but it wouldn't also be a loss here in the engine that I have shown you. Yeah, so for the future, in particular, the considering of the boundary conditions at the wall, that is something we want to work on. And then particularly also what I haven't shown you is, so it's an annular cylindrical combustion engine, but what I haven't shown you is the complexity possibly that the plenum can make. Yeah, where all the injection is coming from, and including that, that will also be an objective for the future. So that's the end of the presentation. Happy to take any questions.
Thank you so much.